Broadcast is now starting. All attendees are in listen-only mode.
Well, hello everyone. Welcome to Mahr's webinar, Gaging Accuracy, One Step at a Time. I'm George Schuetz, Director of Precision Gages. You can reach me at george.schuetz@mahr.com or through my office phone number. I've been with Mahr for over 40 years now and worked in all phases of dimensional gauges. You should keep an eye out for my quality gauging tips articles in Modern Machine Shop. I think you'll enjoy them, and a lot of those tips are the basis for these webinars that we'll be doing. So we have a number of topics we're going to go through today. We're going to talk about what do we mean by accuracy, how gauging accuracy runs hot and cold. We're going to be doing getting ready for making measurements one step at a time, squeezing more accuracy from our gauging situation, and finally, sometimes you just can't get there from here. So let's start out by talking about what do we mean by accuracy. When you can measure what you are speaking about and express it in numbers, you know something about it. And that's the process for making a measurement, and we've talked about that before. But now that we can really understand what's going on, we can start speaking about the language of precision measurement. And dimensional metrology as a language provides the members, all of us, of the industry and means of communication. The language of dimensional measurements is precise. What does precise mean? Well, when talking about sources of errors in a measuring system, it's not uncommon to hear terms such as accuracy, repeatability, and precision used interchangeably, and sometimes incorrectly when you do that. Accuracy, the term itself, is a pretty nebulous term that incorporates several characteristics of a gauge's performance. The best definition that we tend to use is how close the measured value is to the true value. So what's the gauge saying compared to what the part's real dimension is? Now, repeatability, that's the value you get each time from the measuring process. And precision is the ability of a gauge or gauging system to produce the same reading every time the same dimension is measured. So we've got accuracy, we've got a little bit of repeatability and precision. And repeatability and precision are often used interchangeably. They're pretty close, but remember, repeatability are the values themselves, and how close they are determines the precision. A gauge can be extremely precise and still be highly inaccurate. Now, you've probably seen these types of pictures before with targets and dots on them and so forth. And this is the typical example we would see for the common definition of these terms. What I like about this one, it has the spec limits, the tolerance limits, along with the examples of accuracy and precision. So in the case of course, the last one, the one on the furthest to the right, we have all our measurements well within the center of the target, and we have a little kind of a histogram that shows where they're located there and how that relates to the tolerances. So that's a case, of course, where we have accuracy and precision. Second from the right, where we can be accurate or not so accurate but precise, you can see how you get a bias in that situation. So Here's a little bias. The center of this, these results are offset from the target area. So you can see how these terms can work together, and you can get different combinations, and the gauge has the ability to add to these types of errors that you're getting as a result. But typically, we can think of these examples of how the quality of the parts are being manufactured. Because this one has the tolerances on it, we can pretend these are parts being measured. And if this was a manufacturing process, we could say that in the case of the accurate and precise area here, that the process is well under control, the parts are being made to spec, and part-to-part variation is very small. And you can see that that span is using probably about 50% of the tolerance, let's say. But now let's start thinking about this chart in terms of how the gauge is performing. Now we said that that gauge is really doing a measuring process. The swipe principle that talks about the gauge is the standard, the workpiece, the instrument, the people, the environment. That makes up the measuring process. But now what if we try to eliminate some of the variables in that measuring process? Let's eliminate the workpiece, the people, and the environment, and let's see what the measuring process gives us. So let's do that same type of measurement, but let's just use a setting master instead of parts. Let's use a qualified operator, and let's do this in a controlled environment. This is the process for defining what gauge repeatability is all about. Now, if we had that same type of results for that master on that gauge in a controlled environment, I don't know if this would really be good enough for gauge performance. We'd be using up 50% of our part tolerance just on what the gauge performance is. That doesn't leave much error for other things to happen or what the part itself might be. So I wouldn't say that this is a very good performing gauge. What we try and do is we really want the gauge repeatability to be something in the neighborhood of 4%. So we need to have a real tight band compared to what the tolerance limits are. So that can be pretty tough sometimes. Now, once you have the gauge repeatability achieving 4%, now you can start adding in the other variables into your measuring process. Things like we just eliminated: the environment, the part itself variation, things like form and surface finish, variation from the machining process, and the operator skill, or the gauge's ability to hold the part. Now you add all these things together, you get some more variation, and often you will hear the goal of the measuring process needs to be about 10% of the tolerance span. Well, that's what GR&R is all about: gauge repeatability and reproducibility. That's a topic for a future webinar, but I'm just trying to point out to here that the gauge itself has to be performing a lot better than what the tolerances are required to be measured on the parts that are being manufactured. So these can, once you get those tolerances become smaller and smaller, and the need for higher speed parts and better precision in the parts, those tolerances can become very small, and some of the times these are very difficult things to achieve. Now, as we go along this, we can talk about how gauge accuracy runs hot and cold. Now, you can see from this picture here that there's lots of temperature gradients in a room by itself. We got heat sources from the lamp, from the operator. We got some cooling sources from an air conditioner, and we have some stratification that the temperatures are different at different heights in the room. Now that all affects our accuracy or our performance of our gauging. It takes a little while to warm up in the morning, but after a while, it runs great. Well, we're not talking about me there, since I'm kind of up there in age. What's really happening is that gauges tend to have to, especially in a manufacturing area where you come in, the things aren't running yet, the machine's not on, things are going to tend to warm up in the day. So what an operator might be saying is, well, this gauge is a little unstable the first half hour or so that we're working on it, but after that, it seems to work fine. Well, really what's happening there is that the room is stabilizing, the temperatures are becoming the same with the gauge and the master and so forth, and he starts getting better results. And that's not something that's uncommon, and it's something that really should be considered. And in the gauging world, as the tolerances get tighter and tighter, temperature is going to play a key component in the gauging performance. And we can think of dirt being enemy number one in gauging, but it's either there or not. Dirt is either there or it's not. But everything has temperature. Even the most controlled environments, there are some temperature gradients that we have to worry about. And why is temperature such a critical concern? Well, most materials expand with heat, and different materials expand at different rates. Now you can just think about measuring a 2-inch aluminum workpiece that just came off of a machine, so it might be have some temperature added to it from the grinding process or the churning process. And we're going to use a steel frame snap gauge having tungsten carbide contacts, referencing off a steel setting master, and maybe somebody just opened the side door to cool things off in the shop because it was too hot. Well, there's lots of things going on there that are going to influence the performance of the gauge. What's critical is to keep all the parts as close to the same temperature as possible and eliminate fast temperature swings. We're going to try and keep the gauge and the master at the same temperature. We're going to avoid handling the gauge and master any more than necessary. And we're going to keep the gauges away from sources of heat and cold, things like incandescent lighting, heating, air conditioners, and sunlight. What's critical is to especially for micro-inch measurements, we tend to use breast shields, forceps, or gloves may be required to in our measuring process. Now let's get ready for our measuring process, and we can do this one step at a time. Often in one's attempt to make precision measurements, we forget that the metrology or methodology of the measurement is as important as the instrument itself. As a gauge or measuring instrument user, we assume much of the responsibility for the performance of the gauge. Remember, people are part of the swipe process. We need to go over the gauges every time we use them. You know, first thing in the morning, it's a good practice to just do a quick once over to make sure everything looks good. Things like ensuring the indicator or the readout has been checked for calibration, repeatability, things are free running, nothing sticking, looking over the way things are clamped to the test set, the comparator frame, or the gauge itself. Give it the once over. Check for looseness of play in comparator posts, bases, clamping handles, any fine adjustment mechanisms and handles. Looseness is a big enemy. When using portable or bore gauges, be sure to check the adjustment or changeable contacts to be sure that there are no looseness of play. And if the gauge incorporates some type of backstop, make sure that it's locked in place, tight, and at the proper location. The sensitive contact points on some portable gauges might be multiple part types of tips, where wear-resistant tungstite is welded on, or sapphire might be glued, or diamond might be glued in insert. Check so that these tips that those haven't become loose from some previous use, scratched, or even chipped. If opposing anvils are supposed to be flat and parallel, well, you can check them with a wire or a ball test set to ensure that they are still parallel. And one of the easiest chores to neglect is regular cleaning of indicating gauges and bench comparators. Like I said, dirt can be wiped off, you just have to do it. Dirt, dust, grit, chips, grease, scum, and coolant will interfere with the accuracy of gauge blocks, indicators, precision comparators, and the parts themselves. Take the same steps to ensure that the reliability of the master discs or master rings that you're using, or if you're using gauge blocks, examine them for nicks and scratches and scars of rough handling. Finally, if you see a sudden shift in the process during the day, these same basic steps should be part of the troubleshooting routine. Don't just ignore that since there's been a sudden shift that something's changed in the process or so forth. It could be the gauge itself. And even though the gauge has a calibration sticker on it, things happen over time. And you should be aware and observant enough that all these possibilities can happen, and we shouldn't overlook them, but try and find out what's going on. Now, we can squeeze more accuracy from a gauging station. Now, tolerances over the years have really shrunken from the 1940s to now. They've been more than cut in half, and form and surface finish tolerances are becoming a bigger part or bigger percentage of what the tolerances are now. So things have to be done with the gauging process to make sure that we can meet these tighter tolerances. Now, all gauges are engineered to provide a specific level of accuracy under certain conditions. Now, we saw this chart before that gauges have different characteristics, and a hand tool, for example, a caliper, is a measuring instrument. It's very versatile, but it's a little bit slow to operate, takes a lot of operator use to do it right, and the performance or the resolution of that caliper is not that good. And then you can work your way up to fixed variable gauges, something like air gauging or a fixed body plug, that may not have the versatility, but they have good speed of measurement, can be very high performance, and very easy for the operator to use. But with the things happening and changing in the world, manufacturing requirements change. Maybe those tolerances that we used a bore gauge for previously have tightened up. So the gauges that were used at one time for one process may not meet the new requirements on the same parts because they have a tighter tolerance, and certainly they probably won't work on a completely different part. Now, for example, measuring bores on a sample run of engine blocks or pump housings and so forth is completely different than an in-process check on the same bore of when you're measuring literally hundreds in a single shift. And we know tolerances get tighter, and engineers tend to just put those tighter tolerances on the manufacturing process. Now the requirements are for speed, ease of use, portability, data collection, and high performance and accuracy from the gauging process. So an adjustable bore gauge may be acceptable for that sample run of blocks, but clearly it's not the solution for an in-process, high-volume run of parts. So from the previous slide, it's pretty clear that as tolerances get too tight, a variable plug gauge may be the right solution for this new measuring requirement. But even that, when tolerance gets so tight, that could be somewhat of a challenge. You take this one application where tolerances were 1/1000, now they might become 5/10. It's not unusual sometimes over time to see that happening. And people are getting more concerned about the ability to make those measurements, so they want documentation where that gauge now has to pass that 10% GRR that we kind of mentioned before. In our world, that meant that gauge had to repeat now to 40 microinches, pretty tight tolerances. And that's tight even for fixed variable gauging. But, with a little bit of work, you can even make a fixed variable gauge a little bit better and squeeze some more accuracy out of it. By making special engineering changes to that gauge, there's an opportunity to improve the accuracy of the gauge's performance. What you can do is you can reduce body clearance. You can reduce the centralizing area that can influence the readings. Basically what a gauge does is measure the diameter. If there's a lot of body clearance, you can start measuring the chord instead of the diameter. Now that becomes more influential as the bore gets smaller, but by reducing the body clearance, you can reduce that, but still provide enough ease of entry to make much better measurements and reduce part errors. We can also use a tighter tolerance zero master or use master deviation. A lot of people are still in the process of using classes of masters, X and double X's, and which have a deviation to them, but they'll always zero the gauge to that nominal size of the master. But they could be adding 20 or 50 microinches of potential error, potential gauge bias to that measurement. Well, if you start using masters and using their master deviation, you can eliminate that error and improve the gauge performance. You can also choose a digital readout that has the proper resolution for the application. So with some relatively simple design changes, the goals of performance can be met in a lot of applications. It all comes down to knowing the application and what the gauge capabilities are. Again, this goes back to our swipe principle. In this case, we can tweak the instrument and the standard to get better performance. The fixed plug bore gauges reduce operator influence and make it easy to use. And if we had to go a step further, then we might have to look at things like the environment to help us get a better performance out of the whole gauging system. Again, understanding the measuring process can help us make better measurements. This brings us to sometimes you can't get there from here. Over the past 40 years or so, digital indicators have had a big impact on dimensional measurements, especially against dial indicators. Digital indicators offer long range and some very high resolutions, down to 10 millionths of an inch. They can provide direct readings. There's no approximation of reading between the lines. They have the features of a bench amplifier at a fraction of the cost. You can get data output or even wireless data output for process control and documentation. And despite having longer range, you can get better accuracy with a digital indicator. So digital indicators are the way to go. And like I mentioned, with tolerances shrinking, the tolerances that were once plus or minus 2 thousandths are 10 times tighter than that. So we have to work towards gauging that gets us better performance. So it's natural then to try and squeeze a little bit of performance out of a customer's existing gauge by replacing the old dial indicator with a new high-resolution digital indicator. That makes sense. Let's take the old indicator, throw it away, and then we get higher performance out of the system. The thought process is pretty simple. What needs to do this is replace the indicator, get better resolution, and get better performance. While there may be cases where this can improve, most often the replacement causes the user to lose faith in the gauging that they once trusted. What the higher resolution really does is amplify the repeatability performance of the gauge. What was once a slight shift between a grad on the indicator becomes 2, 5, or even 10 flicks of digits on the digital indicator, giving the user a sense of non-repeat and issues with the measuring system. So let's take a look at a typical snap gauge application where we want to get better performance. Now, snap gauges, when they're sold, are typically sold with a dial indicator having an indicator with resolutions of, at the most, 5/10, or typically more like a 10. On the shop floor, when the part tolerances change from 2 thousandths to 1 thousandths or even 5/10, the supplied dial indicator may not have the resolution for the operator to make good decisions as to whether the part is good or bad. The inherent errors in the gauge, and it's a real challenge for the operator to make good measurements. Because every time he puts the part in there, that dial indicator is not going to show him the discrimination that he might really need. And now he might be trying to qualify parts using only 5 grads, for example, of the indicator. So what you want to do here is that there's only ways to get from that dial to digital indicator and get better performance out of the system. And really what you need to do is do a thorough gauge study. Put the digital indicator on there, ensure that you are getting performance. Do some repeat testing. do some GNRs. If the gauge itself does not perform and cannot make the measurements, a step up in gauge performance may be required. And this is where we're going to go from an adjustable a variable gauge with a reference, which is a 300p, to maybe a fixed variable gauge. We have to take a physical change in the type of gauge to get a better performance for the operator on the shop floor. So what I tried to do today is cover a little bit about what we mean about accuracy. We talked about how temperature can influence the gauge performance and some of the things we need to do to eliminate temperature from our measuring process. We talked about how us as users need to be a real part of the measuring process. Check out the gauges before we use them. As we use them, look for strange things that are happening, and just make sure that the gauge is performing the way it should be. Talk a little bit about how we can take a gauge that's meant to be a better step in performance, how we can modify it and make it even work to a better level of performance. And then sometimes we've seen that, even though we can try and improve the performance of a gauge by adding a higher resolution indicator on it, the gauge itself may not be good enough to achieve the results that we need. If you have any further questions or comments, you can always email me or phone me here at Mahr. We're going to be sending you a copy of the webinar in an email shortly, and you'll have the ability to download it and listen to it again and pass it around if you like. So again, thank you for taking the opportunity of attending the webinar, and we hope that you're well and you have a great day.